Hello, everyone. In this section, we will introduce the discrete MOSFET amplifier circuits for the common gate and common drain amplifier configurations. In the previous video, we finished the discrete circuit analysis of the MOSFET common source amplifier. Next, we move on to the MOSFET common gate amplifier. As shown in the circuit, the input signal is coupled to the MOSFET source terminal through coupling capacitor C1, and the output signal is coupled from the drain terminal through coupling capacitor C2. As usual, we begin with DC analysis first. The DC operating point gives us the MOSFET small signal model parameters, which are needed before doing AC small signal analysis. In DC analysis, the signal frequency is 0, so the coupling capacitor impedance, 1 over j omega c, becomes infinite. Therefore, the coupling capacitors behave as open circuits. The resulting DC circuit is shown on the right, and it is exactly the same as the DC circuit used in the previous CS discrete amplifier section. For AC small signal analysis, the impedance of the coupling capacitors approaches 0, so they behave as short circuits. The small signal circuit is shown on the right. At the gate terminal, the bias resistors RG1 and RG2 are equivalent to a parallel resistance. At the output, RD and RL are also in parallel. At the input node connected to coupling capacitor C1, there are two branches, one through RS and the other into the MOSFET source terminal. Therefore, RS is in parallel with the equivalent resistance looking into the source, called RIS. So we can simplify the circuit. The parallel combination of RG1 and RG2 is replaced by RG, and RD in parallel with RL is replaced by one equivalent output resistance. This gives the AC small signal circuit shown on the right. We again start by finding the input resistance, Rin. As before, the input resistance is RS in parallel with RIS. Here, RIS is the equivalent resistance looking into the MOSFET source terminal. Since Ig equals 0, the gate voltage Vg is 0 volts in the small signal circuit. From the T model, we can directly observe that RIS equals 1 over Gm. After obtaining Rin, the input voltage Vin is given by the voltage divider between Rsig and Rin. Therefore, Vn equals Rn over Rn plus Rsig multiplied by Vsig. Since Rn equals Rs in parallel with RIS, this can also be written as Rs in parallel with RIS, divided by the quantity Rs in parallel with RIS plus Rsig multiplied by Vsig. Once Vin is known, the source current Is can be found as negative Vin divided by RIS. Then Id equals Is, and this becomes the controlled current flowing out of the output node. The output voltage is Vo equals negative Id multiplied by the parallel combination of Rd and RL. Substituting Id equals Is equals negative Vin over 1 over Gm, we get Vo equals Gm times Vin times the parallel combination of Rd and RL. After finding Vo, the voltage gain is Av equals Vo over Vin, which equals Gm times the parallel combination of Rd and RL. If RL is infinite, meaning the load is open-circuited, the open-circuit voltage gain AVO becomes Gm times Rd. The overall gain, Gv, equals Vo over Vsig, or Vn over Vsig, multiplied by Vo over Vn. Therefore, Gv equals Rn over Rn plus Rsig, multiplied by Av, which becomes the parallel combination of Rs and 1 over Gm, divided by that same parallel combination plus Rsig, then multiplied by Gm times Rd in parallel with RL. Finally, we find the output resistance Rout. As usual, we set the input signal source Vseg to 0. Then Vin is 0 volts, so Is is 0 and Id is also 0. The controlled source is therefore an open circuit. When a test voltage Vx is applied at the output, the test current Ix equals Vx over Rd. Thus, Rout equals Vx over Ix, which is Rd. Remember that RL is not included when calculating the amplifier output resistance because RL represents the external load or the input resistance of the next stage. To summarize the CG amplifier, its input resistance is Rs in parallel with 1 over Gm. In the usual case where Rs is much larger than 1 over Gm, Rin is approximately 1 over Gm. This is a very small resistance, so it is a drawback for a voltage amplifier. The open circuit voltage gain is AVO equals GM times RD with no negative sign, so the output signal is in phase with the input signal. The output resistance is RD. Finally, the CG amplifier also has good high-frequency response, which will be discussed in a later chapter. Next, we move to the MOSFET common drain discrete amplifier. As shown in the circuit, the input signal is coupled to the MOSFET gate terminal through coupling capacitor C1, and the output signal is coupled from the source terminal through coupling capacitor C3. The drain terminal is connected to AC ground through coupling capacitor C2. Again, we start with DC analysis. Since the DC signal frequency is 0, the coupling capacitor impedance 1 over j omega c is infinite, so the coupling capacitors are open circuits. The DC circuit shown on the right is therefore the same as the DC circuit used in the previous CS discrete amplifier and in the CG discrete amplifier just discussed. For AC small signal analysis, the impedance of the coupling capacitors approaches 0, so the small signal circuit is shown on the right. At the gate terminal, RG1 and RG2 are in parallel. At the output, RS and RL are also in parallel. Since the drain terminal is shorted to ground by capacitor C2, the small signal circuit is not affected by RD. Therefore, we can simplify the circuit by replacing RG1 in parallel with RG2 by RG, and by replacing RS in parallel with RL by one equivalent resistance. This gives the AC small signal circuit shown on the right. Then we substitute the MOSFET T model into the circuit. If channel length modulation is also considered, the equivalent resistance RO is connected between the drain and source terminals. Because the drain is at AC ground, one side of RO is grounded, while the other side is connected to the same node as RS in parallel with RL. Therefore, RO is also in parallel with RS and RL. So we can further simplify the circuit by combining RO in parallel with RS and RL, as shown in the equivalent circuit on the right. We again begin by finding the input resistance, Rin. This is the same idea as in the CS circuit. Since Ig equals 0, the resistance looking into the gate terminal, Rig, is infinite. Therefore, the input resistance is Rg. Also, the source current Is equals Vin divided by the total source side resistance, which is 1 over Gm in series with the parallel combination of Rs, Ro, and Rl. After obtaining Rin, the input voltage Vin is given by the voltage divider, Rin over Rin plus Rsig multiplied by Vsig. After Vin is found, we look at the current path from the input gate terminal to the source terminal and then to AC ground. Along this path, 1 over Gm is in series with the equivalent resistance Rs in parallel with Ro and Rl. The output voltage Vo is the voltage across that parallel resistance. Therefore, by voltage division, Vo equals the parallel combination of Rs, Ro, and Rl divided by the quantity 1 over Gm plus that same parallel combination, then multiplied by Vin. The same result can also be obtained by using Is times Rs in parallel with Ro and Rl. From the relationship between Vo and Vin, the voltage gain of the CD amplifier is AV equals Vo over Vin. This equals the parallel combination of Rs, Ro, and Rl divided by 1 over Gm plus that same parallel combination. Since 1 over Gm is usually much smaller than Rs in parallel with Ro and Rl, the voltage gain of the CD amplifier is usually close to 1. For the open circuit voltage gain, set RL to infinity, so AVO becomes Rs in parallel with Ro, divided by 1 over Gm plus Rs in parallel with Ro. Since 1 over Gm is much smaller than Rs in parallel with Ro, AVO is also approximately 1. The overall gain is GV equals Vo over Vsig, which is Rin over Rin plus Rsig multiplied by AV. Since Rin equals Rg, GV becomes Rg over Rg plus Rsig, multiplied by the parallel combination of Rs, Ro, and Rl, divided by 1 over Gm plus that same parallel combination. In the common case where Rsig is much smaller than Rg, GV is also close to 1. Finally, we find the output resistance of the CD amplifier. We set the signal source to 0 and apply a test voltage at the output. Looking from the source toward the gate, since Ig equals 0, the gate voltage Vg is 0 volts. Therefore, the resistance looking into the source is 1 over Gm. The output resistance Rout is 1 over Gm in parallel with Rs in parallel with Ro. Since Rs in parallel with Ro is usually much larger than 1 over Gm, Rout is approximately 1 over Gm, which is a small resistance. Therefore, the CD circuit has high input resistance, low output resistance, and a voltage gain close to 1. This behavior is the same as the voltage buffer discussed earlier, which is used to solve input resistance and output resistance matching problems. So the CD circuit is a voltage buffer amplifier and is very suitable as the final stage of a multi-stage amplifier. The CD amplifier also has good high-frequency response, which will be discussed later. This concludes the introduction to the discrete MOSFET, common gate, and common drain amplifier circuits. Please look forward to the next lesson. See you next time. Bye.